Assalamu alaikum dear students, we're back with another video lesson. Hopefully this lesson is going to be the last one in chapter 5. Okay, so if you remember last time we were talking about a lot of things. We talked about how a speaker works, for example, and then after that we talked about how a galvanometer works, the base of a galvanometer, and how a galvanometer can be used as an ordinary voltmeter or as an ordinary ammeter, let's say. And then of course we ended up right at this point here. So we're going to talk about or we're going through the section review for 5, or you can say chapter 5, unit 3, or you can say section 3, let's say. So we've solved questions like this one before, so I'm just going through these questions real quick. If there was something new, of course, I'll make a pause and then I'll give you some details about them. So the first one says, a particle with a charge of this much charge experiences a magnetic force which is 1.5 Newton while moving at a right angle to uniform magnetic field. If the speed of the charge is 620 meters per second, what is the magnitude of the magnetic field the particle passes through? So these questions, of course, these are easy enough. We can say, or if you want to go through the questions, we can say this. Remember, basically it asks us for the magnitude of the magnetic field. When the force is given, and it is a particle, of course, you can see that, it is just one. So in this case here, we can just say F magnetic equals to what? Equals to Q V B here. So we want the magnitude, the strength of the magnetic field. Luckily, they don't ask about the direction here. So B equals to what? Equals to F magnetic, or magnetic force, divided by charge, and then, of course, multiplied by the velocity here. You have a magnetic force, which is basically 1.5. You have the charge of this particle. Basically, the charge of a particle is is basically the charge. By the way, it tells you that we cannot use 1.6 times 10 to the power negative 19. That is because they gave you this value, or the value for this particle here. So we do have this one. And then, of course, for the speed, which is 620. You do the math, of course, you'll find the magnitude of the magnetic field strength in Tesla. Okay, and then the next one here, take a look. That is for the direction. It says an electron moving north encounters a uniform magnetic field if the magnetic field points east. What is the direction of the magnetic force on an electron? Remember this, guys. Whenever they ask for the directions on whether a magnetic force on a charge, let's say, always remember this, yeah? Thumb would point the magnetic field. Sorry, my bad. Fingers would point to the magnetic field, you can say. Thumb would point to the direction of the motion. The palm, that would be a magnetic force on a positive charge. The back of the hand would be a magnetic force on a negative charge. So what do we have here? We have an electron. So focus on the back of my hand here. It says what? It says an electron moving north. So you can do something like this. Imagine the board is basically, or the top of the board is north, south, east, and west, yeah? If that is the case, okay, or if not, we'll just do it this way here. So basically that is pointed to the north, okay? That is, let's say, north, okay? And then the magnetic field is directed towards the east, basically, that is east, yeah? So if that is the case here, the force will be, the back of my hand would represent the force on an electron here. So if we use the board, it is going to be out of the board, yeah? But if I'm going to flip my hand so that you get a horizontal component north, east, west, and south, of course, in this case, it is going to be upward here. So the direction of a magnetic force on an electron is going to be upward. Remember this? I'm doing this so that representing north, south, east, and west here. But if I do this, let's say considering the top of the board as north, then of course it is going to be out of the board. That is also considered as upward. Okay, take a look at this one. That is also easy. It says a straight segment of wire. Whenever you have a wire, remember this: magnetic force in wire equals to BIL. Okay, you do know that. So giving the values, plug into the equation, of course, you'll find the magnetic force easy enough. What about this one here? It says two parallel wires have charges moving in the same direction. By the way, it doesn't tell you the current is moving in the same direction, yeah? Or what type of charge is moving, but we do know this. If the charges are positive, if they are moving, that means the current is parallel, or the current is in the same direction. What about if they are electrons moving? Even if electrons are moving, as long as the charges are moving in the same direction, that means the current is still in the same direction. We don't care whether electrons go right, left, electrons, or current will be in opposite direction. As long as the charges move in the same direction, that means the current will be in the same direction in the two wire. And of course, if the current is the same, that means there will be an attractive force between the two. Another question which is also worth mentioning or going through is question 5 here. It says, find the direction of the magnetic force on a current carrying wire as in figure 5.13. That is basically 5.13. Take a look. How do you answer questions like this? Now remember this, whenever you're given magnets, or let's say the poles of a magnet, we do know that, let's say, magnetic field will always go from north to south. So basically the direction of the magnetic field, you can say it is from right to left. And you can see the direction of the current is upward as well. That is the direction of the current. So knowing this too, you can easily find the direction of what? The direction of a magnetic force on the wire as well. So using this, of course, you can say, all right, watch this. So basically, this will be the direction of the current, this is the direction of the magnetic field, and then, of course, this is going to be the direction of the magnetic force on a wire. So if the current is moving like this, so you can say upward, this is the direction of the magnetic field, which goes from north to south. So you can see the force or the wire, there will be a force on the wire, of course, which is going to be outward, or you can say in the positive z direction. Okay, that's not much of a big a deal. This is the summary of this, which is also very important. I would recommend every single one of you guys to go through the summary, because basically going through the entire, instead of going through the entire chapter, you can go through the summary. It gives you an idea, an insight, or it helps you remember the things that you've learned very quickly. And then, of course, if you want to further dive deeper into this, of course, you can go through the concept as well. Now, standardized test preparation. Once again, I might not go through every single questions, yeah, but of course, I'll go through some of the questions that might be important. It says, how can you increase the strength of a magnetic field inside a solenoid? Remember this, for solenoid, we said there are many ways where you can increase the strength of this, yeah? And of course, if you remember, or you can use the equation, by the way, as well, yeah? In order to increase the strength of a solenoid, you can use the equation, but you have to be very careful. There's one thing that is not in the equation. So for example, B equals to mu naught, let's say, Ni over what? Over L. So we can say, by increasing what? By increasing the number of turns, you can say that is one. By increasing the strength of the current, that is also true. And then what else do we have? By, let's say, decreasing the length as well, that is also, we can do that as well. This is the number of turns, by the way, yeah? Magnetic permeability, we consider that because you're using this in the same environment, so we're trying not to change this one. But one thing that I want to point out is this: by using an iron core, let's say, or by inserting an iron core into the solenoid. So for example, if this is the solenoid here, by inserting an iron core, of course, here, it is going to increase the strength of the magnetic field as well here. Okay, so by increasing the number of turns per length, so that is two both together, okay, by increasing this, we can do that, okay? Or you can say separately, by increasing the number of turns, by decreasing the length, that is also true. Okay, increasing the current, that is also true. By placing an iron rod or core inside the solenoid, that is also true. So each, or you can say all of these will be correct in this case. Use the diagram below to answer questions 2 to 3. How will electrons move once it passes into the magnetic field? Once again, you can see this, remember, always do this, yeah? Motion, magnetic field, force on electron, force on a proton. So here we have an electron, so the magnetic field is into, the motion is upward, so you can say the force is to what? To the right, you can say it. So this is basically how it goes. So you can say that is one thing, but remember, if it is going to move, let's say, to the right here, because we don't have right as an option here, we have clockwise and counterclockwise, so you can say this is what is going to happen. Okay, let's get this one back. So it is going to move, let's say, like this, yeah? But if you complete this one here, of course, it is going to be what? It is going to move clockwise, you can say. And of course, this is going to be what happens, yeah? But remember this, since this magnetic field is not complete here, so will it be like a complete clockwise? No, it's just going to be like a semi, you can say, in a clockwise, in a semicircle, you can say, and of course, after that is going to move out straight. Okay. It says, question 3, what will be the magnitude of the force on the electron once it passes into a magnetic field? Now, when it comes to this, a lot of questions will get it wrong. Why? Because since it is an electron, they will just go, let's say, with this option here. Because it is an electron, we do know that the charge of an electron is negative, so they immediately choose this one. No. remember this, it says the magnitude, okay? So just the value, like how much the force will be on an electron, not the direction of the force. So whenever it says the magnitude, please make sure that you underline or bold in this one here. Whenever it says a magnitude, that means no direction, no positive, negative is concerned here. We just want the value. So in this case, the correct option is going to be QVB, that is the magnetic force here. Please be aware of this one because you might make mistakes here. Okay, so not B, the correct one is A here. Okay, now as for this one, this is easy enough as well. Okay, you have basically the charge, you have the speed, you have the strength of the magnetic field. Says find the what is the magnetic force, right? The equation QVB, magnetic force, QVB, and then of course do the math, you will find the answer. All right, for this one here says use the passage below to answer the questions there. A 25 centimeter long, by the way, since you have length, always convert it to meter, SI unit. We have a current of 12 ampere, current from, let's say, east to west of Earth's magnetic field and all that, yeah, location, whatever it says, and is directed from south. What is the magnitude of the magnetic force on the wire? Whenever it's wire, magnitude of the magnetic force, F equal to BIL, okay? Magnetic field strength, current, and length. You do the math, of course, you will find the answer. What is the direction of the magnetic force on the wire? Of course, it is going to be down towards the Earth. Don't forget to use the right-hand rule. And of course, this is easy enough. We've been through this a lot. Now, another question worth going through is this one right here. It says, use the diagram below to answer questions 7 to 9. All right, so the first one says we have two wires, basically. The current in each one of these two in opposite direction. One of them is downward, the other one is upwards. Says wire 1 carries current I1, as you can see here, creates magnetic field of B1, you can say. So this one here creates B1 here. And wire 2, of course, creates magnetic field of B2, you can say. Okay, current 2 and magnetic field B2. What is the direction of the magnetic field of B1 in the location of wire 2? Now this is, you have to be very careful here. Remember this, wire 1, this is normally wire 1, yeah? If I draw a magnetic field around wire 1 here, what would be the direction here? Remember, the current is moving downward. If that is the case, so remember this is the direction of the current, so here's what you're going to do. So in this case, I can say, so it is going to move, let's just say clockwise, but you have to be very careful here, guys. Not this one. You have to be very careful. When I say clockwise, that is at your point of view, but normally this magnetic field, it is not something that it looks like clockwise. It's basically horizontal, concentric horizontal lines, you can say. So let me see if I can draw a little bit better. Perhaps something like this one here, yeah? Maybe this one would make more sense to this. All right, or to you. So this is basically going to be the direction of the magnetic field, which is going to be in this direction here. But if we use red so that it is more obvious, so it is going to be moving like this. All right, now what about wire 2 here? Where's wire 2? Here is wire 2, guys, okay? So this is basically wire 2, okay? So wire 2 and wire 1. So at this point right here, what would be the direction of the magnetic field right at wire 2 here? So if I'm going to do this one here, watch this, guys. So this is normally wire 2, and this is wire 1. So the magnetic field is going to be like this one here. So if I do this one here, you can see at this point right here is going to be something like this one. So if I'm going to, remember this, always you can say draw a line that is tangent to the circle. If that is the case, of course, it is going to be outward here, which in this case is going to be towards the, say, positive here. Okay, that is right at this point here. So this wire is basically, if that is the case, watch this, if this is wire 1, is going behind wire 1 and then come out right at wire 2 here. So at this point, it is going to come out like this, or you can say perpendicular to this one right here, or you can say in these directions. So of course, it is going to be out of the page here. Okay, what is the direction of the force? Now, before that, yes. Now the second part says, what is the direction of the force on wire 2 as a result of wire 1, okay? So remember this, these two are repelling one another. And how do we know they are repelling one another? Okay, now perhaps we can redraw this one. Let's say this is wire 1, I'll just do with one circle here. The current is going downward, so here's the direction of the magnetic field. As for wire 2 here, the current is going upward, but the current is basically, if that is the case, here's what is going to be Okay, so here's going to be the, you can say direction of the magnetic field here, yeah? Because if it is going upward, this is what it is, and then this is what it is. So if these two are in the same direction, that means they are repelling one another. So the question is, what is the direction of the force on wire 2? So wire 2, of course, is going to be repelled, yeah? Okay, as a result of wire 1, why wire 1 will be repelled? Because this magnetic field, of course, is going to repel it. Imagine if we only have one wire. As long as the current can pass through the wire, there will be a magnetic field around the wire, and this wire, of course, will not be pushed or repelled or attracted or whatever, pushed or pulled, yeah? Of course. But as soon as you bring another wire that carries current, of course, then of course these two magnetic fields will cause a force on one another, especially if they are in opposite direction, they repel one another. So this wire will be repelled because of this magnetic field here. And of course we can say this wire will also be repelled in the other direction because of this magnetic field. You can say B2, and this is because of B1 here. Okay, next says, what is the magnitude of the magnetic force on wire 2 here? By the way, we've mentioned this before. So we said magnetic force, let's say on a wire, that is basically BIL, yeah? Remember, we're talking about wire 2, so that is going to be F2, we can say. These are current in wire 2, length of wire 2, but this force is created by B1 here. So which one of these is going to be correct? Of course, that is option C. What if the question was F, or the magnetic force on wire 1? Of course, it's going to be B2I1L1, okay? Because the magnetic field of one wire causes the force on the other wire, and this note is also very important. Okay, and this is easy. We've went through this one here. This is also another easy one as well. Now here it's for this one, it says short response questions. These are proton, let's say charge of a proton, mass of a proton, magnetic field, moves a clockwise circle with a tangent speed of this much as well. What is the direction of the magnetic field? Explain how could you determine this as well. So remember this, because it is a proton and because it moves in a clockwise circle, then of course finding the direction is very easy. So whenever we said previously, whenever something moves in a circle, always clockwise, yeah? So here's, let's say, clockwise. So let's say we're at a point here. If it is clockwise, this is the direction of V. That is one thing. And the force is always directed towards the center because it is clockwise, yeah? So remember, we have a proton, so positive charge, you can say. Okay, and of course, this direction of the motion, and this direction of the force, you can say. Okay, magnetic force. Then, can you find the magnitude of the field strength, the direction of the magnetic field strength? Of course, is going to be very easy, yeah? So watch this. The force is downward. Remember, it's proton, yeah? So the palm of your hand. And this is going to be the motion, yeah? So how can you do that? This is basically the direction of the motion if I do something like this, right? So basically, that is going to be the direction of the force, and this is the motion, so the field is going to be outward, you can say. So the direction of the magnetic field is out of the page. That is one thing easily, yeah? You don't have to go through a lot of detail there. Okay, as for the magnitude, or what is the radius of the circle? Whenever it says radius of the circle, always remember this, you'll have to do something, yeah? Magnetic force, right, must equal to what? Must equal to centripetal force. You do know that magnetic force equal to what? Equals to QVB. I don't have, I should have wrote it here. So magnetic force equal to centripetal force, but magnetic force equal to QVB, and then centripetal force equal to what? V squared, you can say, over the radius, yeah? And of course, you can find this radius over there. All right, so that is, and then you do the math, of course, you will find the answer. Take a look. These are some Zhyar questions similar to what I have just explained. These are very important, of course. All right, now a few more past Zhyar questions. These are recent ones. I would recommend you to go through all of them. I might not go through all of them as well. All right, it says the solenoid has 3,500 turns. Remember, if the number of turns per unit length is 5,000 turns per meter, calculate the length of the solenoid. This is easy enough, yeah? Remember this. I'll just do the equation, you do the math for yourself. Okay, so we have number of turns per unit length equals to what? Equals to 3,500. Watch this. Says if, so, no, not this one, okay? So it says solenoid has the number of turns is 3,500 if the number of turns per unit length is 5,000. So this is 5,000. The number of turns is 3,500. Yeah? Can you find the length? Yes, of course, you do the math, and of course you'll be able to find the length, and that's it. Okay, and then as for the second question, the magnitude of the magnetic field of the center of occurring current circular coil is inversely proportional to which one of these? Whenever you get questions like this, always write the equation, because unless you write the equation, you might not know it. What do we have? We have a coil, yeah? So the magnitude of the magnetic field, yeah? So of course, B for coil. Do you remember the magnetic field strength for coil? That is, of course, was mu. Yes, what was mu? Ni over what? Over 2r. So you can see these are all directly proportional, but this is inversely proportional. So the question says inversely. Is it number of turns, electric current, or radius of the coil, or both? It is radius of the coil. Okay, now, what else do we have? It says electrons inside two straight parallel wires. We've solved questions like this. These are easy enough. Now, remember, if you remember the previous lesson, of course, we went through these questions. It says how to convert a galvanometer into an ordinary voltmeter that could measure high potential difference. Of course, we said if we're trying to connect with a galvanometer, you have to connect a resistance, a very big value with, let's say, in series, of course, with the galvanometer. So by connecting a resistor of, is it very low? No, it has to be. So you can cancel out these two directly. It is either C or D, yeah? By connecting a resistor of this one in parallel, it is not in parallel, so it is in series. So that would leave us with answer or option D. When you break a magnet in half, this is easy enough. There's always two, you can say, poles always, no matter what. A region in which magnetic force can be measured, this magnetic field strength, yeah, or just magnetic field. To convert a galvanometer into an ordinary meter, you see, these are super important. A device is to convert sound waves into or to electrical signal, that is also important. A device used to convert sound waves into electrical signal. So is it a microphone? Yes. Is it a laser? No. Generator? No. A galvanometer? No. All right, as for this one here, how about I'll try to solve question 9 for you as well. Then we'll see how many more questions we'll go through as well. All right, so take a look at this. Let me scroll this one up so that we can still have the options on the screen. Okay. So let's do it here. Okay, now what is this question about? It says what? A proton travels with a speed of this much at an angle 37. So we have a proton that is moving, right? West-north of a magnetic field of this much and all that, yeah? Determine the magnitude and direction of the magnetic force on the proton. So this part, or this question, has two parts. How about we write the information that is given first? So we have a speed of, so V is 3 times, because of too much reflection, I can't see very well. 3 times 10 to the power 6, that is basically meter per second, that is the speed. At an angle, so we have theta, which is 37 degrees, west of north, forget that one for a second, a magnetic field. So we have B, which is 0.3 Tesla, and then points to the north. This is Q of a proton, mass of a proton, determine the magnitude and direction of the magnetic force. So magnetic force, both magnitude and direction as well. That is first part. Second part says on the proton's acceleration here, yeah? So second, find the acceleration. So let's do first thing first. So how do we find the magnetic force first? Magnetic force on a charge, of course, we do know that, QVB, yes? That is one thing. Okay, so what is the charge in here? By the way, no, don't forget this, because you're given sine here, so of course you need to add sine theta as well. So in this case, 1.6 times 10 to the power negative 19 times V is basically, what was it? 3 times 10 to the power 6 multiplied by B, or magnetic field strength, which is 0.3 Tesla, sine 37 degrees, yeah? So do the math, of course, you will be able to find the answer, which is going to be this much Newton. And of course, is going to be, now what about the direction here? Perhaps I'll get a calculator and do this one, just to get precise answers, because as you can see here, do I have my calculator with me? Oh, yes. All right, let's use this one perhaps. Okay, So what do we have? We have 1.6 multiplied by 10 to the power negative 19 multiplied by 3 times 10 to the power 6 multiplied by 0.3 multiplied by sine 37, correct? Yes, so the answer is going to be, let's erase this one now. The answer is going to be 8.666, which is about, we can say 7. All right, 8.7 times 10 to the power negative 14. That is the magnitude. What about the direction? Okay, now let's do the direction as well, yeah? Watch this. The speed is basically this much west of north, okay? So west of north in here. The magnetic field is basically pointing north. So this is west of north, that is going to be this much. Remember this. This is the angle basically, but we're using the vertical or the component that is perpendicular to that. So we can say this is the direction of the motion. What is going to be the magnetic force? It is a proton, yeah? So magnetic field here, you can see, this is the field and this is the motion, so it is going to be into the page, you can say. But if we're given north and south and all that, so of course it is going to be downward here. So this is downwards. That is basically the magnetic force. Now we're going to use this force to find the acceleration. How do we do that? Okay, so let's do the acceleration here. Remember, because it says find the acceleration, whenever it says find the acceleration, that means magnetic force, it is equivalent to, you can say, the force in translational motion. So in another word, we can say this magnetic force here equals to mass times the acceleration. So we have this, we have the mass of proton, we can find the acceleration. Acceleration equals to magnetic force, which is 8.7 times 10 to the power negative 14 divided by the mass of a proton, which is 1.7 times 10 to the power, where is it, 20. This one has to be negative 27. Please add a negative here. Okay, so 1.7 times 10 to the power negative 27 kilogram. And of course, we can find the answer to this. So let's find the answer to this one as well. Okay, so the answers to this one is going to be 5.117 something, or we can say, which is very similar to 5.2 here. So the acceleration is basically going to be 5.2 times 10 to the power, that is basically 13, it's meter per second square, you can say. So basically, which one of these options you can see here? The force is 8.7 times 10 to the power, this is negative 14 by the way, negative 14. Let's write this one nicer, make it smaller, 8.7 times 10 to the power negative 14, don't forget. Which one of these options is this? The force is 8.7 times 10 to the power negative 14 downward. So we have basically this and this, this and this. There's 8.7. The force is downward, but this one says upward, so not this one. And then the acceleration is going to be 5.2 times 10 to the power 13. So the correct option is going to be option A here. Okay. And okay. When a charged particle is moving perpendicular to the magnetic field, its path, of course, is going to be what? It's going to be, you do know that it's going to be circular. Is it going to be circular? These options are repeated here, shouldn't be repeated. Parabolic or horizontal, of course, is going to be circular. The magnetic field effects effect on an electrical charge in a uniform magnetic field is maximum when the angle between the direction of the moving electron and the direction of the magnetic field, that is basically 90, because sine 90 is 1 here. And of course, the remaining question is very, very easy. Okay, so you can see all the other questions, we have went through them as well. Take a look at this one. Says, in which situation the direction of the magnetic force on a proton moves in a magnetic field is out of the page. I believe we've solved questions like this one as well. How about let this be the last one, since it is about direction here as well. Okay, so take a look here. This one, it says the direction of a magnetic force on a proton. Proton, that is the palm of your hand, you can say. So for this one here, remember, if I do this, that is into, yeah? So of course I'm going to do it upward here, you can say, or something like this one, yeah? So if that is the case, the motion, the direction of the magnetic field, that is outward, so it is going to be out of, or you can say upward here. That is the case, okay? It says out of the page, yeah? So not this one here. This one is, you can see that the magnetic field is downward. The motion is to this side, so of course this one is going to be out of the pitch. So B, keep an eye on this one here. Let's just keep this one in mind. Okay, and then what about C here? Remember, it is into the pitch and it is upwards. Of course, it is going to be to the left side, you can say. And this one here, you can see that it is into the pitch. So of course, we're left with the only correct option, which is going to be D. And of course, we've solved questions like this one. These are super easy, or you can say very easy questions, of course. And okay. All right. So take a look here. I believe these are basically what we have. These are the answers as well, but I believe one of them here, question 9, of course, this one is going to be A, just in case. Okay, of course, this one is going to be updated soon. But just remember this. I should keep this on the board as well. This is supposed to be A. Okay. And then I would really recommend you to you try the rest and solve them on your own. So basically, that was the last lesson in chapter 5. Soon, inshallah, we're going to continue with the remaining chapters. So make sure that you go through all these concepts. If there is anything you haven't understood till this point, please make sure you rewatch the videos, and then, of course, you practice or solve a lot of questions regarding that concept, because the sooner you fix the problem, the better. Because if you leave it, of course, it's going to pile up. And then maybe at the end, you're not going to catch up with all of this, or it becomes too much. And of course, you think you might not be able to do it. So don't, okay. Make sure you keep practicing, and I'll see you soon, inshallah. Assalamu alaikum wa rahmatullah.